Hi everyone, welcome back. If you're watching this video, I'm going to assume you're either studying for your Unit 5 test in class or you're studying for the AP exam. In any case, this video is going to help you with Unit 5 of AP Chemistry, which is all about kinetics. This unit covers topics such as rate laws, half-lives, molecular collisions, and reaction mechanisms. As always, the link to my video script will be in the description, as well as any sources I use to help me study for this unit. Let's get into it. Unit 5.1, reaction rates. So reactant rates are basically just how fast all of the reactants in a reaction turn into products. Mathematically, it's negative change in reactants over change in time for reactants. Side note, here it's negative because the reactants decrease into products, making its rate of change negative. For product, it's change in product divided by change in time. The relative rate for reactions is decided by the coefficients. So for a general reaction, AA equals BB, the rate is -1 over A times A divided by T is equal to 1 divided by B times B over T. Be sure you remember stoichiometry from prior units. So here in this photo, you can see that if you ignore all of the random words, as reactants decrease, products increase. The slopes on this graph are the rates of change, but there are different kinds of rates. The average rate is the rate calculated over a specific time interval. The instantaneous rate is the rate calculated at one specific moment in time. The initial rate is the instantaneous rate calculated at time equals 0. Often questions will ask you about the initial rate. There are a few things at the particle level that affect reaction rates. This includes concentration, where more particles in an equal volume, resulting in higher collisions, which means higher rates. Temperature, which means there's more kinetic energy, resulting in higher collisions. Surface area, where more particles are exposed, resulting in higher collisions. And catalysts, which offer a different way for particles to react, resulting in higher collisions. More about all of this will be later in the video. Unit 5.2, Introduction to Rate Law. Rate law states that the initial rate of a reaction depends on the concentration of the reactants. Rate is equal to K times A to the M times B to the N, where rate is equal to change in concentration over time. K is equal to the rate constant, which depends on the temperature. A and B are molar concentrations of reactants, and M and N are reactant orders for each reactant. There are three main rate orders you'll see on the exam, and here they are for you to study. The general concept is if concentration changes by A, then rate changes by A to the M. To find the overall reaction order, just add all of the exponents together. To find this rate law on the exam, there are a few steps you can follow. You'll be given several trials, so find two trials where only one of the reactants has changed. Then compare how much it changed by to find the exponent. For example, if A triples and the rate increases by 9, then its rate is second order because 3 squared equals 9. Earlier for the rate law equation, I mentioned the letter K is the rate constant. What this actually tells you is how fast a reaction is. A higher K value means a faster reaction. Only temperature can change the K value. Rate is always measured in meters per second, so K must balance out the other side of the equation. An example of this is a second order equation having a K value of meters to the -1th times seconds to the -1th. Unit 5.3, Concentration changes over time. Okay, so you already know what a rate law is, but an integrated rate law tells you how the concentrations of a reactant changes over time. On the exam, you'll only see 0th, first, and second order reactions. Remember to never guess reaction order based on stoichiometry. It's based on experimental values. Here's a chart for everything you'll need to know about integrated rate law from lumasource.io. As you can see, the 0th reaction has a linear line. The first order reaction has a logarithmic line, and the second order has an inverse line. You may look at this chart and think, what is the half-life? It's the time any species takes to decay down to half of its value. So, for example, lead-210 has a half-life of around 22 years, which means it takes lead 22 years to decay down to half of its original sample size. Only first-order reactions have a constant half-life. Unit 5.4, Elementary Reactions. An elementary reaction happens in one step. It goes A plus B, then to products, representing just one collision between A and B. Molecularity is the number of reactant particles involved in this elementary reaction. Unimolecular means only one particle changes, so A to products. Here, the rate is first order. Bimolecular means two particles change, so A plus B to products. Here, the rate is second order. Finally, molecular, means three particles change, so A plus B plus C into products. Here, the rate is third order. It's worth noting that elementary reactions stop here because it's incredibly rare for four particles to all collide together at once. It's even quite rare for three to collide, hence why only 0th, first, and second orders will actually be on the exam. As a reminder, the coefficient in front of a species in the reaction will be the exponent that's part of its rate law equation for the elementary reactions. Another note, products are not part of the rate law reactions because the rate law focuses on how fast the reactants can turn into those products. Unit 5.5, the collision model. Reactions happen because particles collide with one another and then bonds get rearranged as they collide. In the collision model, particles move at random, collide with one another, and then only react if the collision is successful. There are three rules to determine if a collision is actually successful. First, particles must actually run into one another. Duh, they have to collide for the collision to happen. Second, activation energy is the minimum amount of energy needed to break bonds. So the kinetic energy of the collision must be greater than or equal to the activation energy in order for bonds to actually be broken. Finally, third, the particles must collide at the right orientation. So the atoms that were going to form the new bonds must collide with one another and come together. There are a few factors that are able to increase the amount of collisions. Concentration and pressure, because as more particles get squeezed into the same area, they become more active, meaning they interact with one another more. Temperature, because particles become more active as temperature increases, because kinetic energy increases, so they often interact with each other more. Surface area is another common one, because more reactants are exposed as you increase surface area, which means particles interact with each other more. Now we're gonna get to the good stuff. I took this course 2 years ago, and I remember this graph so vividly. So here's the Maxwell-Boltzmann distribution graph. It displays that the energy of particles is higher at higher temperatures, although the area under each curve is the same because they have the same number of particles. Another graph for you. This is a reaction energy profile, which I'll go more in depth to later. It shows the peak of the graph for the reactant energy level is the activation energy. Earlier, I mentioned that catalysts offer another way for reactants to react, and this is important because they also lower the activation energy. Since catalysts offer more chance for a reaction, the activation energy decreases, as you can see on this energy profile here. Unit 5.6, Reaction Energy Profiles. Okay, so as I just mentioned in 5.5, the reaction energy profiles show the change in total energy, or enthalpy, as a reaction progresses. The x-axis is the reaction completion, not time. It's how complete the reaction is. Then, the y-axis is the potential energy. So, the reactants are on the left. They have a constant energy level right here. Then, the peak of the graph shows the transition state, where bonds are all moving around. On the graph I drew here, it's separated by with and without a catalyst, so don't get too confused. Then on the right side are the products with their own constant energy level. In an exothermic reaction, which means energy gets released, products have less energy than reactants. In an endothermic reaction, which means energy gets absorbed, products have more energy than reactants. The graph I have here shows an elementary reaction, where it completes in one step. But if you see a graph with multiple peaks and valleys, which I'll go more in depth to later, then it's a step reaction completed in more than one elementary step. As I mentioned, as you can see on the graph, the activation energy is decreased with the catalyst present. The overall energy change in the reaction is represented by this equation. Change in H for enthalpy, is equal to energy of the products minus energy of the reactants. For this unit, I would recommend looking at the Arrhenius equation. Sorry if I'm saying that wrong. It's not specifically on the test, and you won't have to memorize it, but it's kind of the underlying concept, and it will help you if you need more explanation for this unit. Unit 5.7, Introduction to Reaction Mechanisms. A reaction mechanism tells you the steps of elementary reactions needed to get to a final product. There are four main components of a reaction mechanism, being products and reactants, which you already know what those are, intermediates, which is a product in one elementary step, then a reactant in the next, but it doesn't appear in the overall mechanism, and a catalyst, which is consumed in an early step and regenerated in a later step, but it also does not appear in the overall reaction. For a mechanism to actually be valid, it has to follow these two rules. All of the elementary steps must add together to show the full reaction, and the rate law from the slowest step must match the experimentally determined rate law for the overall reaction. This slowest step is called the RDS, the rate determining step, which I'll talk more about later. For this subunit, it's important you remember the molecularity I mentioned earlier in Unit 5.4. Unit 5.8, Reaction Mechanisms and Rate Law. As I just said a second ago, a reaction mechanism shows the steps of elementary reactions within a full reaction. It can have four components: products, reactants, intermediates, and catalysts. Remember that the coefficients in a reaction show the rate law for that step. So A plus A equals product, so rate is equal to A squared because there are two A's present. The rate law for the full mechanism is only the rate law of the slowest elementary step present. If this rate law matches the experimental one for the mechanism, then the mechanism is valid. For FRQs, you must know how to do all of this. Unit 5.9, Pre-equilibrium approximation. The rate determining step, or RDS as mentioned in 5.7, controls the rate of the mechanism. If you see a step labeled fast with a reversible arrow sign, then there's an intermediate present there. To derive the rate law, we have to follow these steps. First, write the rate law for the slow step. Second, identify the intermediate present. Third, write the expression for the reversible step. Fourth, substitute step 3 into the slow step's rate law. Here I have an example of these steps in action for you to see. Unit 5.10, Multi-step reaction energy profiles. Okay, so in 5.6, I mentioned that if a reaction energy profile has multiple peaks and valleys, it shows a step reaction, which is multiple elementary steps combined. To go over some of the vocab for these types of graphs again, the transition state is the local peak. The valleys represent any reaction intermediates, and the RDS corresponds to the highest peak, aka the highest activation energy. The slope will show the overall energy of the reaction, where if the reactants are higher than products, it's exothermic, and if the reactants are lower than products, it's exothermic. A good thing to know for FRQs, a reaction with X number of elementary steps will have X number of peaks in the graph. Unit 5.11, Catalyst. Okay, so once again, to go over from prior subunits, a catalyst gives reactants another path they can take to react, usually being faster and requiring less activation energy. There are a few different types of catalysts though. A binding catalyst binds to the reactants and forms a new intermediate. An acid-base catalyst donates or receives a proton, H+, from a reactant, creating a more reactive intermediate. A surface or a heterogeneous catalyst has reactants that bond to its surface, holding them in the correct orientation to bond with others. Alright, so that is everything you will need to know for Unit 5 of AP Chemistry, which is all about kinetics. This unit appears more on FRQs, so it's pretty important that you can visualize and draw everything as well as explain the concepts here. Personally, this is one of my favorite units because it relies more on that visual aspect than having pure memorization. Anyways, thanks for watching, and be sure to comment with any questions you have down below.